Today I will introduce memory and short channel effects. Let's see the memory part first. There is uh, normally two types of memory, and first one is SRAM and second one is DRAM. The SRAM is normally composed of 6 transistor. There is 2 CMOS inverter and 2 transistor next to the CMOS. Because there is no capacitor in the SRAM, so its speed is very high, and then there is no electronic pass between the VDD and ground, so it has low power dissipation. It is static when power is applied, so SRAM means static random access memory. The next one is DRAM. It means dynamic random access memory, and it is composed of 1 transistor and 1 capacitor. When we open the transistor, when we close the transistor, the cap can be charged, and then we can save the electron on the capacitor. Because there is capacitor and charge and discharge behavior, it operates very slowly, and we have to refresh the capacitor. So refresh is needed. Because we have to refresh the capacitor, so it has high power dissipation. Next memory is flash memory. It is only 1 transistor, but it has floating gate between the control gate and substrate body. When we give the high control gate voltage, we can write the data in the floating gate. When we write the data, we can use tunneling, the Fowler-Roderheim tunneling, or hot carrier injection. When we want to erase the data, we also using a tunneling effect. Next is the short channel effect. There is many short channel effect, but today I will introduce 3 short channel effects. The first one is punch through. Punch through is very critical to short channel devices, so it is very important part of the short channel effect. Let's see the device structure. When the device becomes shorter, it's the source to body depletion region and drain to body depletion region has overlapped, so it makes the another pass, electron pass between the source to drain into the body. This makes the transistor the poor subthreshold swing. Originally, the transistor behaves like this step function like ideal transistor, but it becomes poor things. Then how can we solve this problem? First, we can increase the substrate doping, and then we can minimize the depletion region, and then we can depends the punch through. But uh, but today devices doesn't increase the substrate doping because of the random dopant fluctuation. We do not use the increasing method. Okay. There is another way to defend the punch through. It is silicon on insulator SOI. We make the silicon oxide the insulator between the gate and body under the source and drain. This makes the band diagram like this, and then we can physically defend the path to pass, so we can defend the punch through. This oxide makes quantum well like behavior, so but it has many problems. The first one is self-heating problem. Because we defend the path between the source to drain, so there is no heat sink, so the carrier becomes more heated, and its temperature becomes bigger. The second one is series resistance problem. Because we defend the path between the source to drain, the resistance becomes high, so it drives the device's speed lowered. The third one is it is very high cost, so we do not use this method on the commercial market. There is another problem called hollow implant. We can highly doped hollow implant between the source to body and drain to body, so we can defend the punch through. Also, it is very high cost, so we normally do not use this method. The second short channel effect problem is a VT roll-off. When the long channel, the barrier is very high, so the path, when the off current, there is no path to source to drain. But when it becomes a short channel, the gate barrier becomes lowered, so it is easy to electron jump to source to drain. It makes the VT roll off, so we called this effect VT roll off. Likewise, when the drain bias becomes bigger, there is another problem called deburr, the drain-induced barrier lowering. When the device is long channel, we can't see the variation between the VD equal 0 and VD is bigger than 0. We can't see, it is not change much, but when the device becomes shorter, we can see the variation very big, and it is critical to devices barrier. We can easily see the barrier reduced. So this called deburr problem. Thank you for watching my video.